Hello, everybody, and welcome to our chapter 4. This is kind of a little bit of a joke here, 4 and 3/5. It's sort of a subset of chapter 4, but chapter 4 and 3/5 on relative motion and 2D kinematics. And it's really going to be more on relative motion this time around. 2D kinematics is going to be what we get into in the next chapter in projectile motion. But relative motion is what we're going to mostly focus on in this segment or this set of videos. So in order to understand relative motion, you need to understand what a frame of reference is. And that simply means, a frame of reference simply means from your point of view. Our description of a frame of reference is, you might say, a coordinate system, all right, that whereby you measure position, velocity, acceleration, or so forth. But a good way to sort of illustrate this is, say, to look at the sun. All right, is the sun moving over the course of a day? All right, so here's our sun right here. It's going to be, I'm going to make it orange. All right, and over the course of the day, so here's the Earth down under. It appears that the sun is moving through the sky. Right, rises in the east and sets in the west as we look south. All right. That is our frame of reference. As our frame of reference is based on the Earth right here. So it looks like the sun is, moving around the Earth. In truth, you know that that happens because the Earth is actually rotating and we're moving more around the sun than the sun is around us. So based on your frame of reference, that would determine how you perceive the motion of another object. But it's based on a certain coordinate system. It's based on some certain, like I said, a frame of reference. Our coordinate system, for the most part, is based here on Earth. So if we see anything else moving with respect to the Earth, we say, oh, that thing must be moving. We don't really consider the fact that our coordinate system, our Earth itself, may be moving. That's a large-scale example, but it applies to smaller things as well. All right? Two objects can be considered to be in the same frame of reference if they are moving with the same velocity or rotating around the same axis. All right? We're not going to be talking about rotating too very much, but moving with the same velocity, same speed and direction. Let's say you and another car, so your car is red right here, and you're on the turnpike, and you're both heading, I don't know, west. All right, so the other car is kind of next to you right here, and you're kind of neck and neck. You're both going the same direction. The other car is going this way, as are you. All right. You're in the same frame of reference. Why is that? Well, as you in your red car, as you look over towards the person next to you in the blue car, you don't see them moving if they're in the lane next to you. I mean, they might be moving. They're probably passing you, or maybe you're passing them. But if you're going at exactly the same speed and in exactly the same direction, you can look at the people in the other car. You can wave at them. You appear not to be moving. So you're in the same frame of reference, so to speak. All right? We're going to talk about frames of reference that move with a constant velocity. You can talk about changes in acceleration as well. We're going to talk mostly about just constant velocity in this course. But it all goes back to the concept of a frame of reference. That is, you're moving with respect to what? All right? So we're going to illustrate that and give that a notation right here. And this is our notation. All right? In most cases, we're going to be dealing with velocities right here, and so that's why we have a velocity vector written out. But look at this notation system. There's some subscripts here that are very important. A and B can be any two objects. A is the object that is moving, and B is the object that it is moving with respect to. So think of object B as being at rest. All right? Object A is moving over object B, or moving with respect to B. So, for example, if we looked at the sun example, again, so here's our sun right here, kind of moving through the sky, and here's our Earth right here. From our point of view, from our reference point, we would say the sun has a velocity. The velocity of the sun with respect to the Earth is something, whatever that would be over the course of a day. Okay, velocity of the sun, the apparently moving object with respect to the apparently stationary object. Now, again, we know in real life the Earth is moving and the sun is mostly stationary. but from our point of view, we see that sun is moving. So the first object is always going to be the one that is moving, and the second object is always going to be the object that is apparently at rest. Okay? So if a car travels 25 miles per hour north, it moves relative to the earth or relative to the ground. So you might illustrate it this way. Velocity of the car to the ground, that's CG. Again, these AB right here are just placeholders. They can be anything. Invent your own initials, if you will. In this case, C is for car and G is for the ground. So the velocity of the car with respect to the ground is 25 miles per hour at north. And that's what that vector would be right there, that relative motion vector. All right. But what's also true, we can take those subscripts and we can flip them around. All right. So we say that a car, I'm going to draw a red car again. All right. A car is moving at velocity of the car to the ground equals 25 miles per hour at north. All right. VCG right there, car to the ground. And here's the ground right there, okay? From this reference point, the assumption is that the car is moving and the ground is stationary. But what's also just as true is that you can say this. You can turn that around. You can have the car here, and you can say, all right, well, let's pretend that the car is stationary and the ground is moving backwards under the car. So this is the ground down here, and of course the red is going to be our car. Car. So if we were to do that, we would have to put a minus sign in front of it. So if we say the velocity of the car to the ground is 25 meters per hour north, we have to say the velocity of the ground with respect to the car equals 25 miles per hour at south, or east or west, or whatever the opposite direction is. Okay, so that's what this main point is right here. If we change the order of the subscripts, we have to put a minus sign in front of it. All right, whatever the original direction was, changing the subscripts, or changing the reference point, you might say, changes the sign out front. Now, it's kind of ridiculous to think of the ground moving underneath the car. We know that for the most part the cars move over the ground, but think of maybe as a treadmill. All right, with a treadmill, you actually have, some pulleys right here, and it literally does cause the ground to move underneath you. So a treadmill is a really good example of this. You can move over the treadmill surface, or the surface can move under you, but you're going in opposite directions. All right. So why do we care about the order of subscripts right here? Because if we want to add vectors together of objects that are moving kind of in different reference frames, this right here that I'm about to circle or put a box around, this right here, you need to put a star next to that, you need to underline it, you need to highlight it. Whatever it is, this is very important, because what we're saying here is if we're adding two vectors together to get a third vector, what are all these 1, 2, and 2, 3 all about? Well, it's like saying the velocity of object 1 to object 2. All right? Actually, before I do that, let me give you an example so you can sort of follow along. Here we have an orange truck right there, and it's a flatbed truck, and it's moving over the ground. Okay, so the truck is going to be object 2, we'll say. Okay, that's object 2. The ground is going to be object 3, and a person walking on the truck is going to be object 1. So here's our person. Not a very good person, but they're walking on the truck that way. Okay, and the truck is moving forward, like so. All right, so the truck has a velocity with respect to the ground. So that's the velocity of the truck to the ground. The person has a velocity with respect to the truck. Velocity of the person to the truck. So what we might want to find out is, what is the velocity of the person to the ground? All right, so say we're given this, How do we add them together to get the velocity of the person to the ground? Because the person is going to be moving faster than they would normally move on 2 feet, because the truck, the surface they're walking on, is in fact moving. So we put it in this order. Let's say, for a second right here, I'm going to see if I can blot out some of these. Yeah, I'm going to do that. Okay, that, and this right here. 1 to 2 plus 2 to 3 equals 1 to 3. That's certainly true, but I'm going to write it a different way. If we want to find the velocity of the person, oops, I think I have too thick of a, there we go. Person to the ground. That's going to be the sum of the velocity of the person to the truck, so P to T, plus the velocity of the truck to the ground. See how this is object 1 to object 2? So yeah, our person, I forgot to put, is object 1 right here, okay? So it's 1 to 2, person to the truck, plus 2 to 3, the truck to the ground, equals 1 to 3, the person to the ground. That's the order in which we need to add things right there. We can say 1 to 2 plus 2 to 3 equals 1 to 3. Or A to B plus B to C equals A to C. However you do that, this is the order that we need to do things in. 1 to 2 plus 2 to 3 equals 1 to 3. And if our subscripts are not in that correct order, if they're flipped around like this, if the subscripts are in a reversed order, we need to do a little bit of extra work to flip them around and get them in the right direction so that we can add them in this format. But this format right here is going to be very, very important. Okay? All right, I'm going to end this section in about 30 seconds. One thing I want to do just to kind of finish out is to show you a video clip that illustrates relative motion. All right, now this is from a movie called Top Secret. It was back in the 80s. It's sort of a spoof, kind of a comedy type movie. And this one guy goes to, I don't know, to Germany when it was still in Nazi Germany or something like that. Anyway, it's a big gag right here, but the gag here is what's called the train scene. All right, and see if you can pick out what's going on right here. So can I play? Let's see, I'm trying to play this here. There we go. All right, I'm going to play it first with sound, and then I'll go back and sort of comment on it with the sound turned off. Okay. Oops, I need to rewind it. Okay. It's only about 30 seconds long, so this is kind of interesting. Relative motion, frames of reference. All right. Okay, did everybody catch that? All right. Again, sort of a tongue-in-cheek, sort of a gag right here. All right, but of course you see what usually happens before trains move is that they're setting you up right here. And the actor, by the way, this is Val Kilmer right there. He sells it pretty well. He even kind of jerks backwards a little bit, like the train is moving. Right. But you don't realize the train is not moving, but the platform is, until you see the third frame of reference right here, the ground. So in truth, the train that he's on is not moving at all with respect to the ground, but this other kind of rig is, that rolling rig. So anyway, that's a train scene from Top Secret. I hope you liked it. And that's going to be the end of this segment right here. All right? Thanks for following along, and I'll see you on the next one when we're going to be getting into some examples. See you on the next one.